That's it. So we learned how to perform a t-test. It's performed exactly the same way as a z-test. So that's the good news. The only difference is how much information that you have. So we're going to learn about the t-distribution and when degrees of freedom are used, what is meant by a confidence interval for the population mean and how is it computed, how to perform, oh, we're not going to do this. I moved this morning. And how to increase power in a study. So we went over all of this last week, well, most of it. So this is what we've been doing. So this is a nice little review. You know, the z-test is when we have perfect information about any population. And this is the mean of our sample minus the population mean over some standard error of measurement. This is any test statistic we do for the rest of the semester. It's some difference over some measure of error. Now, we teach you this and we start here because it's the easiest to understand. But the truth is, except when you're dealing with like large data sets like the SAT and the GRE, we usually don't have this population mean or standard deviation, standard error that we can compute. So when we use the z-test, when the population mean and the standard error is known, and we use the t-test when the standard error is estimated by calculating the standard deviation of our sample. So in order to do a t-test, you have to be given this stat right here. This is the standard deviation of our sample. Just like the z-test, the t-test, oh, hold on, Jackie's coming in. The t-test just compares two means and then puts it over a standard error. So this is known, and these are just big buzzwords that you have to start to get used to. This is a parametric test, and when we do z and t stats, that is inferential statistics. And here comes Sim. So again, you don't have the standard error, let's put of the population. And you might not have the mean of the population. So we know that we don't have enough information. We absolutely need the t-test. 2, and I realized this was a little confusing, so I'm spelling it out here. And you'll see me write this different ways, so I want you to find a way that is comfortable to you. T, critical, or T star, I tend to write T star, is a number that you get from a table, okay? It's your critical value. Remember, it marks off your rejection region. The table that we'll be using for T is in today's notes. So I've given you the Z table in the past. And now we go to the T table, which is a lot easier to read. So that's the good news. The T table gets easier. So we have T critical, which is critical or T star, that you always find from a table. T calculated or T obtained, or you'll see me write test statistic. This is what you are calculating. Okay, any questions? No? Okay. So there are 3 types of t-tests that we are going to be going over. Are you ready? There is a one sample t-test. That is when we have, and this is what we're doing today. This is when we have one sample of data and we are finding out information about it. Next time we meet, we're going to start down 2 sample t-tests. One is independent, where you compare this class to another class of students. Each class has nothing to do with each other. Then we have something called dependent samples. Dependent samples are when we either match pairs, or the easiest way to remember it is pre-test, post-test. That's usually the easiest one. So you have 2 columns of data, but it's the same people are involved or they've been matched in some way. So sometimes sibling data or twin studies are considered dependent samples. Sometimes they're not. So those are the 3 types that we'll be learning. Okay, performing the one sample t-test. So this gets really easy. So just like we've been doing, and I have 1, 2, 3, 4, 5, 6 examples to go through with you guys tonight, set up exact same way. So we set up H sub O and H sub A. In fact, we do that pretty much for the entire rest of the semester. We then we select an alpha, typically 0.05 is used. We get a critical value of T, ready, from the table. Some of you are getting very confused about this, so I'm going to just keep spelling it out. Degrees of freedom, word to the wise. Degrees of freedom are the same for the Z and the t-test, the one sample t-test. They're both n-1. Once we move on, you have to be really careful. And I'll spell it all out for you. But for your 2 sample t-tests, dependent or independent, they change. Sometimes we do n-2. Okay. So just like in the Z hypothesis testing, we obtain appropriate value of T critical from the T table in the book. I've given you the one that I find is easiest to use. Okay, now we have assumptions. I think I had a slide on assumptions for the Z test, but like no one really talks about the Z test. For the T test, we talk about assumptions a lot. You have to have a random sample of interval or ratio scores. Remember, a lot of what we do is dependent and theoretical on the fact that we've selected our sample randomly. The raw score population, which we will never know, forms a normal distribution. And I know that sounds really like ridiculous, but that's what all of this is based on. The only reason why we can do any of this is because we lean on the theory that the raw scores are normal in the population. And the standard deviation of the raw scores is estimated by computing, and this is in the wrong spot, by computing the standard deviation of the sample. Remember, we did a lot of those, right? So you just compute, it's not the variance, it is the standard deviation. This is the square root of the variance. Any questions? No? Okay. So again, this is just going through some of the computation for the t-test. I don't know why it says computational formula. So we have to first find the standard deviation and the variance and the standard deviation of our sample. So you guys have done this enough. And here is T obtained. See, T obtained, OBT. X bar, that's X bar of our sample minus the mu, whatever we're comparing it to. And you have to really keep your wits about you here, over the standard error of the sampling distribution of the means. So we compute, here's the standard error, and then we use it in the denominator of the t-test statistic. Now, yeah, that's okay. Any questions? Okay. So for those of you who are going on to higher courses, I just wanted to include a slide so that you understood that once again, we are comparing the T distributions, okay? So the T distributions, technically, they're a little bit higher. Sometimes they can be a little bit wider, but they have just like values of T, like we saw with values of Z. There's a whole bunch of X bars in here, and we're comparing these two distributions to one another. And this is an example. Now, last week, I gave you the critical values that you will use for Z. Again, we can't do that with the with the T stats because it always comes from a table. But don't worry, we'll walk you through that. So we have T critical based on a degrees of freedom and then a T obtained. And then just like with the Z statistic, we have effect size. So everything is the same as it was for the Z statistic. So Cohen's d is the mean difference, the mean minus the population mean, over the sample standard deviation. This is where most students run awry. They pick some other number. So don't get too confused. It's the sample standard deviation. It's not the standard error. It's because then you'd wind up with another test statistic. Percentage of variance explained. This is new this week. I have to put it back in the homework too. I forgot that this slide was in here. I love the study of variance explained. So we will see this in SPSS. Percent of variance explained is a different way to measure effect size. It is the percent of variability that is accounted for by knowing what you got. So you have a set of variables, and how much variability in the scores is explained by whatever treatment your subjects went under. And all it is, it's your test statistic squared over your test statistic squared plus your degrees of freedom. So again, it's just another effect size. Population mean. And then remember, our goal is we don't really care about our sample. What we want to do is we are all about estimating the population parameter. That is it. That is our goal. So it's really nice to think about, well, you've got it for your sample, but the sample is not going to do us any good. The sample is only a small sample. We want to break these out. And again, I always bring up the example of the COVID vaccine because it's something we all just went through together, whether you chose to get vaccinated or not. They did the testing on a small sample, but then they wanted to blow up the results and talk about the larger population. And you can imagine I can tell you about a million things that went wrong, but that was as good as they had, right? So that's what they went with. But we wanted to estimate, okay, what's going to happen in the general population? If we vaccinate all these people, how many people in the population are still going to get sick? And given also that this is medical testing and it's right in the beginning of, we're still in the infancy stage of that virus, we still don't really know. There are two ways to estimate. So the first is point estimation, and the second is interval estimation. So a point is, it describes the actual point where you think mu is going to fall. I always bow to interval estimation. I don't know why, I just always have. That's the way that I was taught. And that's just a confidence interval. So I know this looks a lot scarier than it actually is. So we're going to walk through it. Just like this is nothing different than what we were doing last week with the Z-stat, okay? So this is our standard error. So take note if you're confused. This is the standard error that you already calculated way back here. So you see, you pull that coming forward. And then I lost my place. Okay. This is the critical value of T from the T table. Now, if you're paying attention, you remember from last week that I said when you have a confidence interval, so we can test in a one-tailed test, and you'll see in the examples today, test in the one-tailed test, which is great, but your confidence interval critical value is always the two-tailed value. So let me show you. And this is going to take some time to sink in. So you'll see the T table is broken out into one-tail values and two-tail values. You can use this for your test of significance, your hypothesis testing, but then when you come back to your confidence interval, you always come to the other side. You're always using a critical value from the two-tailed test. And why is that? Because the confidence interval has two sides to it. It has a plus side and it has a minus side, or it has an above and it has a below. So we always use the two-tailed value. Put a big note. Then this is mu. So this is what we're estimating. The best estimate we have of this is the mean of our sample. And then this side is exactly the same as this side. So on this side, it's our mean of our sample, the critical value on the other side, the positive critical value, and then the standard error again. So it's negative critical value, positive critical value, all circulating around this mu. So we leave this mu written as a notation, and we estimate, and we put the mean of our sample in there as well. So this becomes a plus minus, and I did the plus, you'll see this in the examples. Okay, maximizing power. Oh yeah, one other announcement that I have to make. I couldn't come up with, well, I didn't have time to come up with, I'm gonna do an individual lesson on power. So some of you indicated, it seems like, okay, good. So apparently what's in the book and what little I did last week is not enough to cover you guys. So give me through the weekend and I'll have a lesson on Power Up. So yeah, I just wanted to say that. So I'll have my, I'll have charts and graphs or whatever I come up with. So, but at this level of training, it is really important that you understand from a theoretical standpoint, how do you maximize power, right? So large differences, we maximize power with large differences in the independent variable, meaning don't implement a yoga program unless you know it's going to really make an impact, right? You've done some research on it, like a weight loss program. You wouldn't decrease someone's calories by 100 calories a day to make that's a draft. By the way, I'm not making any comments about what you should and shouldn't be doing to lose weight. I'm just saying, like, you want big effect. Okay, you're going to eat 10 calories a day and you're going to eat 2,000 calories a day. Like, you want something that is substantial. You want to give 10 hours of homework and no homework, or you want to stress someone out to the nth degree and put someone in, like an isolation chamber with no stress. Make sure your difference is substantial. So you also want to make sure when you are selecting, a lot of power comes from selection, but you want to make sure that there's little variability in your raw scores. So you want to make sure that the people in your sample represent the population as best as you can, and they are the ones that you are only going to talk about. So don't select from a population unless you're going to talk about all of the people in that population. And then a larger N. The more subjects you have, the better off you will be, hands down. So if you have, and I keep using these as the benchmarks, if you have over 30 subjects, closer to 100, you will be infinitely increasing your power. Don't quote me on the infinitely one, but your power will automatically go up. So those are the three big theoretical points of power. Any questions now on the t-test? No? Okay. So let's go through, believe it or not, that's all that there is. So the t-test, like I said, is an awful lot like the z-test. So that we don't really have to worry about. But as we then take the jump forward, we are going to have to really understand there's a lot more math involved, but the Z and the T are very close. That's why this class I concentrated. You will never see this many examples from me again, because like I said, this was like a PhD dissertation that I did for you guys. Okay, so again, for the t-test, our steps of hypothesis testing are the same. If we find significance, we do these four things. And we'll get to this I removed R squared. I got to put that back in. And then what I did was, this is the table. Again, I like you guys to have the information in lots of places because I know you always lose it, right? I mean, when I was a student, I lost everything. So this is all the APA format for all hypothesis tests, but I pulled out this one t-test because that's what we're working on today. These, I'm not going to pull up SPSS today because there's no need for us to do that. But these are the steps that you walk through with SPSS to generate the t-test. Remember, with the z-test, we do not use SPSS. We got a freebie. I mean, you can, like, if you read through the book and some other professors make you calculate z-scores, but you really can't do anything with them. Like, there's no point. So, but the t-test and moving forward, we are right back in that world. This is the t-table. So I don't like to say, I usually say it's almost gen proof. That's what we call things around here in my house. Like, it's really hard. Like, that's why I've been using this one for a long time, because like, you really can't screw this one up. Some of them are very complicated. There are two sides to it. So if you're doing a two-tailed test, so if you're, yeah, this is the not equal to, or if you're doing a confidence interval, you use this side. Down the left-hand side are your degrees of freedom. So we didn't use degrees of freedom. With the z-test, now we use them. On the
Would you ever have like a percentage and a degree of freedom? In which case, would you like take the average between the two? Like if it was 1.5, would you have to, or are we always just doing full values for degrees of freedom and just looking it off the table?
degrees of degrees of freedom are always based on number of scores.
Okay.
So you can't have 0.5 scores.
Okay. Okay. Yeah.
Like 2.5 kids, right?
Yeah. Okay.
In theory, it's great, but it's impossible to actually do that. So
Okay,
yeah, you
that
always
makes sense.
degrees of freedom are always going to be whole numbers. So you can see two-tailed test, here are your critical values for 0.05 and 0.01. And on the other side for one-tailed test, 0.05 and 0.01. Put a big sign in your notes that when you have a negative less than H sub A, and there's two examples for you today, you have to go in, you use the one tail value, but you switch it from positive to negative. Okay, Sim is nodding. I don't know where Ashley and Jackie are. Colin, Isabella, do you guys get that part? So you see, this is the T critical in the positive. If you're going to be testing a one-tail test down here, you just flip the value to the negative. I know it sounds a lot easier than like, oh, sure, that makes sense. And then you have no idea what we're doing. Don't worry. Okay. And again, this will make a lot more sense as we start to move a little bit. So now all we're going to do for the rest of class, this is all we got, is I have 6 examples for you of all this spelled out. So what I did was I have context for every problem. I have the data. I have the SPSS that we're going to go over. And then I have written out the steps of hypothesis testing. And if we rejected, I listed out Cohen's and the p-value. Okay. So we're going to walk through these. So in this first example, now I also give you the answer in the top. Why? Because that's how I was able to keep track of them. I needed some way to keep track of them. And this is a famous example. I've used this forever teaching. The government claims that cars traveling past your house average 55 miles per hour. But you think they travel much faster. You steal a police radar gun and record the speed of the next 9 cars that pass your house. With alpha equals 0.05, can you claim that the cars going by your house are faster than what the government states? So did anyone watch Modern Family as a show? Okay, do you remember when the mom was demanding the stop sign? That's what this example always reminds me of. I love that. I love that because I'm kind of that mom. Like I'm that hothead. So, and I've done crazier things than that. So, you know, this person is like, their cars are speeding. I want a stop sign and I'm going to steal a radar gun. And now I'm going to record 9 cars that pass by. So now we all fully understand exactly what the example is asking us. However, just to be clear, because you're in my stats class, there is a huge problem with this type of sampling. So what are some of the problems with this type of sampling? She's taking the next 9 cars that pass by the house.
So,
Anybody?
like, it could depend on time of day. Like,
Right?
so you could be in traffic time and your 9 cars are going to be going on an average higher than other times. So if you're trying to do an average, yeah, you're going to see some different values based on that. Or it's rush hour and it's, you know, bumper to bumper and the cars are going a lot slower. Like it could go in either direction, but if you're taking that not time period and 9 in a row, they're all going to be impacted by the traffic that's impacting that area.
Great. Anyone else? There's a couple of others. Weather. So if it's raining, cars are naturally going to be going slower. And the last one that, I mean, I could probably come up with a lot if I really thought about it, but the other one was day of the week. Day of the week and actually month of the year. So if you do this the week of Christmas on Christmas Day, that's very different than if you're doing it on Tuesday in May when everybody's off to work. So you have to, as researchers, you have to think about all those things. Like, I'm not going to take the first 9 cars I see at 10 o'clock. You probably got a bunch of little old ladies going to the grocery store. Just like you're not going to do it at 5 o'clock in the afternoon when everybody's rushing home during rush hour traffic. Okay, so so the first thing that I'm going to do or the first thing that I already did in each example is I ran the SPSS right away so that I can show you exactly where you get all your stats from. So the first thing that you get is what we've seen before. You get how many scores you put in, good checks and balances. You always check this against the number of scores you put in. So if you think that you had 15 people and you only wind up putting in 9, this is going to tell you. It then calculates the mean, gives you the standard deviation of these scores, and gives you the standard error. So you can see this is terribly easy compared to computing it yourself, as long as you know what each of these pieces mean. This is the one sample t-test. SPSS has now run the one sample t-test for you. This is important, and you will see in my notes, we are comparing our results with a mean of 55. If you just put this in with a test value of 0, SPSS will compare, is this different than 0? And more than likely that will be very significant, but that doesn't give us any information. So you impute this, and I tell you in the outline the steps exactly how to do that. So good check and balances, you always make sure that you put in a test value here. So this is your T obtained. SPSS took this mean minus this test value over this standard error and computed your t-stats, T obtained for you. This is your test statistic. These are your degrees of freedom. We know for a one sample t-test, n-1. These are your p-value, which I'm going to get into in a minute. And then we don't pay attention to any of this. Okay, Cohen's d. This is your effect size. So this is your point estimate of Cohen's d. And I calculate it so you guys believe me that I know what I'm talking about, which I think is always important. Okay, so that's what pumps out of SPSS for you. Anyone have any questions on that? No? The biggest question is, what do we do with all the other information? We do nothing. Unless I've circled it or pointed to it, it's really not that important right now. I mean, we could go on forever about the difference between Cohen's and the correction and confidence intervals on your point. We don't do that in this class, but we just can't pick and choose what SPSS tells us. Go ahead, Sim.
We haven't done how to run this in SPSS yet, right?
The directions are right here. I wasn't going to bring up SPSS, but if you want me to go through it, I'm happy to.
No, I was just, okay, got it. So we're going to follow those directions in order to get these values. Got it. Okay.
Yeah, it's not that different. The biggest difference is you're just going into a different menu, but I feel like you guys can handle it. And if you get stuck, just let me know. I can always put up a little video of it. And I'm happy if you're really at the end, hey, could you just run through one example? I would be happy to. Okay, so now let's look at, remember, SPSS prints out this nice little printout with all these numbers. It really doesn't make any decisions for you because it is a computer. So you need to go in now and still walk through the steps of hypothesis testing. Let me just check one thing. Confidence. Okay. So I typed this out the first time and realized it was quite cumbersome for me to keep doing that, even if I copied and pasted. So this is the first time that I typed it out. Okay, so H sub O, mu equals 55. There isn't any difference. Any difference that we see is just due to error. There's no difference between our group and what the government says that the average speed is. H sub A is what the crazy mom believes. She believes that the car speeding by her house is greater than 55. So in other studies, any difference is due to treatment, meaning you've got something. Your group is different. Then we set alpha. So here we just set it at alpha equals 0.05. And then we define the critical values. So degrees of freedom and -1. Our T critical, which is from the table, is 1.860. Always from the table. Now, again, this part of this steps 1, 2, and 3, this is your contract. This is when you are setting up a research study, this is set long before the research study. In fact, this is done in your proposal and it cannot change. So you cannot say, oh, look at this. I have a test statistic that's going to blow it out of the waters at 99%. So I'm going to change my whole test and then I'm going to have 99% accuracy and I'm going to be able to, you can't do that. Like you picked 95, you got to stick with 95. Okay, now we calculated our test statistics. So SPSS, you will notice 2.475 is right here. It's the same one that we obtained. We compare the critical value to the computed test statistic. So here's T obtained, and we see that it falls in the critical region. So it falls out here. So we reject. We can't look up P in the table. P is the percent of scores beyond our test statistic in the tails. And if P is less than alpha, we've got significance. So I did the P value down here. Our P value is 0.019. Where did I get that from? Right here. 0.019. This is a one-sided test statistic, right? We're running this as a one-sided test. This is where you really have to keep your wits about you. One-sided test, so 0.05, which is alpha, is greater than 0.019. So we are correct in rejecting. The p-value acts as another test. Now, I can look at printouts and say, and this is not because I'm smarter than you, it's only because I've been doing this for 20 years, but I can look at printouts, look at the p-value, and determine significance right away. And you guys will get there, whether you want to or not. Okay, confidence interval. This is the formula, same one that I gave you in the slides. So this is our standard error. This is our T critical. Now remember, it's going to be different than this T critical because this has to be 0.05, but two-sided, two-tailed. So we go back into the table, plus 61, this was our mean, and we wind up with a confidence interval of 56.334 to 65.886. I was running out of room because I typed this. So this means that we are 90, this is the interpretation of the confidence interval right here. 95% confident that the mean of the population is between 56.334 and 65.886. That's how you interpret the confidence interval. Our Cohen's D, 61.115 minus 55 over 7.41. And that is 0.82. You will notice we got it right here. Same thing. So that's the good news. You really like when your calculations match what SPSS does. So we have a large effect. And then our p-value. Again, I already went over that. And then here is how you can say this in APA style. And now we can start to include effect size. I don't think I did that in all the examples, but you can even include effect size. Okay, so questions? No? Either this is going swimmingly well or you guys are completely lost. So I'm going to say that you probably don't even know what you're confused about yet, but we're going to move on. Okay, so now this was one tail positive, we rejected. Now we're going to do a one tail positive, fail to reject. So all I did here was change the speeds to get a different test statistic. So the government claims cars traveling past your home average 55 miles per hour. You think they are going much faster. You get a radar gun and record the speed of the next 9 cars that pass your home. So here's the speed. So I reran the analysis with new data. by the way, I should say the implications of this research are that she would get her stop sign, right? Because she rejected the cars are going faster. Now the cars are going slower. We still have 9 scores. Now our mean is 58.8889. Our our calculated T is 1.492 with 8 degrees of freedom. If this is the p-value, for some reason with this one, if this happens to you, just note it on your printout. SPSS would not print out 1 tail and 2 tail for me. I have no idea why, like I couldn't figure it out. Moving on. This is how you write out the steps of hypothesis testing for this one. Mu equals 55, mu is greater than 55, and we have 8 degrees of freedom, and our test statistic now is 1.860. We run our study. Test statistic, I'm sorry, our critical value of T is 1.860. We run our study. Our test statistic is calculated, and it's 1.492. This matches the SPSS printout. However, 1.492 does not wind up in this critical region. Therefore, we fail to reject H sub O. And then I listed a little bit more about p-value. I already knew from the printout with this p-value 0.174. 0.05 is less than 0.174, therefore we fail to reject. And here's how you would write this up if you were writing this up for APA. Remember, I will turn into a pretty big stickler about the context of the problem. So while you can cheat this and write something incredibly small and simple, the proper way is to include your research into the APA write-up. Cars traveling past the house, mean equals 58.88 with a standard deviation, are not statistically significantly higher than 55 miles per hour. Our T calculated was 1.492, our p-value 0.174. Now remember, I talked about that even if your research isn't significant, you still could write up your research results and get them published. You can still help someone in some way. Okay, so that is one example. In one instance, we reject. In one instance, we fail to reject. So now Crazy Mom, in example number 2 here, does not get her stop sign. These cars were not found to go slower, faster than what the government says. Okay. Now these examples here was when our critical region was up here in the positive side of the distribution. Now we're going to move to 2 examples where the critical value is in the negative region. Okay. So a teacher, this is a really funny example. A teacher is interested in whether her students are generally dissatisfied with a new reading assignment. Most kids will be dissatisfied. The teacher administers a survey that asks students to rate their satisfaction with a reading scale, with the scale of -10, very dissatisfied, to 0, satisfied or not satisfied, to +10, very satisfied. The teacher observes the following n equals 24 scores. So we've got 24 kids. I cut off the last score for you. I'll have to put that in. Test against a neutral score of 0. So normally kids on reading assignments get a neutral score of 0. So we want to see, are these guys, she believes that they're going to be more dissatisfied. Sometimes when we're writing out our hypothesis, we have to look for clues in the writing. So this is dissatisfied. Oh no, I didn't. This should be a 23 up here. Okay, good. One sample statistic. So I entered all the data. This is the SPSS data, just like in the last 2 examples that I gave you. This is how many scores I entered. This is the mean and the standard deviation and the standard error. So you can see this is like getting redundant, right? These are all, this is looking the exact same way. Here's what's critical though. This test value, while it is 0, I got it from the problem. So don't forget, put a big note to yourself. Test value, this was put into SPSS. And again, if you don't put one in, SPSS will assume it's 0. Here's your test statistic, your degrees of freedom, your p-values, and here is your effect size. So H sub O, mu is equal to 0, right? Nothing has changed with this data. H sub A, mu is less than 0. She wants to know if they are dissatisfied. Our alpha is 0.05, degrees of freedom are 22. And we saw those right here, degrees of freedom are 22. So our critical value from the t-table is negative 1.717. We run our study. Now I cheated a little bit and I did not list all these out for you because I was getting exhausted. So I got this right from the printout. Our test statistic is negative 2.504 and we reject because it falls beyond the critical region. And we can also look at P on the printout, 0.01. 0.01 for a one-sided t-test, which is smaller than 0.05. So we are good to go to reject. Students are not happy with their reading assignment. That's essentially what you're saying here. Remember, it is critical that you understand this context. So if you just say something like scores are lower, you're, just calling it in at that point. Now, I ran the confidence interval at 0.01. So I ran just to give you guys lots of examples. So I ran this as 0.05. I ran the confidence interval as 0.01. Your T critical at 0.01, 2 tails. Oh, confidence interval is always 2 tails. Your T critical is 2.819. This is your calculated mean from SPSS, plus or minus standard error. SPSS calculated this for you as well, even though you do know how to do it. And then your this is your critical value from the table. And through the brilliance of math, we get negative 1.9565 plus, sorry, this should be plus or minus 2.202. We get a range of 0.2455 to 4159. The interpretation, because I ran this as an alpha equals 0.01 confidence interval, I am 99% confident that the population mean for these students is between 0.2455 and 4.159.
Were these interpretations also APA standard? Like, is that how you would want us if?
No, you wouldn't write it like that.
Okay.
This is just, please understand how a confidence interval works.
Given the context of the problem and what are we saying? Yeah.
Yeah, I don't make you guys do APA for confidence intervals.
Okay.
We're really just trying to, trust me, I had 20 students last semester at Rider, and I think on the final, like 5 finally got it. Like the APA is something you got to hit yourself over the head with a lot to remember it. So I was a little disappointed, but made some adjustments for this semester. Okay, so effect size is tricky. Let's go back up. Remember, we're getting the effect size from Cohen's d, right? Right here, point estimate on the printout. So the question is, effect size, we have a negative 1.9565 minus 0 over the standard deviation of the sample, 3.7474. You could say, hey, where did you get 3.74? And it is the standard deviation of the sample. It is not the standard error of the mean. Standard deviation of the sample. But now we get an effect size that is negative. You can't have a negative effect size. Effect size doesn't work that way. So we take does everyone remember absolute value? Absolute value essentially says you get rid of any of the negative, and your effect size is now 0.522. This is a moderate effect. So you cannot report a negative effect size. So APA style, right here, the satisfaction score of students, and you could even put with their reading assignment, mean, this is the mean obtained, and the standard deviation is significantly less than 0. Your T calculated is negative 2.405, and your p-value is 0.020. Now, I just want to stop here for 1 second and say that if you are, I know you're all going to diligently review this during spring break next week. If you don't know where I got one of these numbers from, do not panic. All the numbers are on the printout, right? So I've had students call me like crying, damn near crying, like, I don't understand where these numbers come from. And I'm like, look at the printout. I didn't pull them out of the air. Like, they're all very logical from the printout. So everything in this sentence right here is right from the printout. The only tricky part is you need to remember, which is why I give it to you so many times, that we are here, how to write it out for the test statistic with the t-test for the test statistic that we're using. Okay. Okay, where was I? One tail positive, one tail negative reject. Okay. Did that one? One tail negative fail to reject.
Effect size so far that we've been looking at is just the D, which is from the slide in chapter 8. We're not yet looking at like the R square, like that effect size, right?
Nope.
Okay. Just want to make sure I'm not confusing myself.
Yeah, I took that out for today just because we have a lot of confusion. Oh, I'm sorry, we have enough. I didn't want to add to the confusion. We're going to have to add that in eventually. Okay. Okay. One tail negative fail to reject. The following is a list of toys sold by the TNK company over a 12-month period. I picked this example on purpose because you have to kind of switch your thinking. A new manager believes that the sales in the first month of 2016 were statistically significantly less than the average in 2015. His sales in the first month of 2016 were 31,456. Now, what you are technically comparing is his first month of 2016 with all of 2015. But we are going to run this as a one-tail test. So, I'm sorry, a one sample t-test. So this, in a sense, acts as our population parameter. This is our mu. This is our test value right there. Okay, so I entered all the data. There it is. Testing at the 0.01 level. Like, why not? We haven't done one of those, I don't think. Okay, so printout exactly the same. N equals 12. It gives us a mean. These are also, I picked this example because it's bigger numbers. We haven't had one of these. One sample t-test. Here's our test value. Here's our test statistic, degrees of freedom. Here's our one-sided p. So we already know, I know, that p is greater than 0.05. So we're going to fail to reject this one, but we will continue on. Our point estimate is again negative, Cohen's D. Let's go into the steps of hypothesis testing. Okay.
What in our confidence interval, shouldn't that be 99, not 95%?
Where?
Where you have the output from, because you said it's 0.1, right? 0.01 instead of 0.05.
For this
We're
example?
testing it. Yes.
Well, we're going to fail to reject, so we're not going to do a confidence interval.
Okay.
Yep. So test at the 0.01 level. If you get significance, you continue on.
Okay.
Okay. Is he correct or down? So you can see the type of leading questions that I'm asking here, right? Is he correct? Are sales down? So let's see what happens if we want to be 99% correct. Let's see what happens. So our H sub O is mu equals 31,456. And our H sub A is that we are less than. He believes we are less than. You can actually run this as a positive test if you really think about it, but it's fine. Degrees of freedom is 11. Uh-oh. I wrote 0.05 here. I wonder what this is. Hold on.
wondering if you were looking at like SPS because when I tried one and it's always doing it at the confidence level of 95 percentile. We have to change that to tell it to do a confidence level of anything else.
We don't do confidence intervals on SPSS.
Okay.
Yeah, don't pay attention. We always do those by hand.
Okay.
Let me just see. Oh wait, I have my printout here. So this is one tail positive, fail to reject. I'm just double checking my test statistic for you guys. Oh, I can do that right here too. Let's see. Let me go back to it so I don't confuse anybody. Failed reject. Okay. So I said here to run it 11 degrees of freedom, one-tailed. I said run it at 0.01, and this is, okay, critical mistake that I don't want you to get confused about. I said in the wording to run it at 0.01. I ran it at 0.05. Okay, so just this test statistic, I'm sorry, this critical value, negative 1.76 is for 0.05. The critical value at 0.01 would be negative 2.718, if anyone wants to do that. Okay, doesn't matter anyway, we're failing to reject in both places. So our p-value is greater than 0.05, so we fail to reject. When we fail to reject, we do not do confidence intervals, we do not do effect size, we write it up in APA style just because I'm making you, and we move on. So toy sales for the first month last year are not significantly less than 31,456. T with 11 degrees of freedom equaled negative 1.861. P equals 0.060. You'll notice also when people write up APA style, you pretty much in this little tiny paragraph right here have all the information to understand everything that went on in the study. You know how many subjects they had because you have the degrees of freedom. So if it's a one sample t-test, you add 1 to it. And once you know this p-value, you know whether or not you are critical. So that's it. Okay, so that is one tail fail to reject in the negative. Let me just make some notes here. I'm going to let you guys catch up for 1 second. Think of questions. There's an error here. Oops. And then I'm going to change that to 0.05. Okay, do you guys think of any questions before we move on? No? I mean, is it making sense? Like, that's why I try to give you so many examples so that something at some point sinks in and you have lots of examples then to look at for your homework, because this is exactly what you're doing for your homework. Okay, two-tail reject. So now we go to testing. Oops, man, I hate when that happens. Now we go to testing in the two-tail. This is what we've been doing a lot of. I know that I gave you all the information for one tail for Z-scores. We really just talk about it with two tails most of the time. But let's look at this example here. In a classic procrastination study, an intro to psych class students received a survey that measured procrastination. This is hilarious. Participants were instructed to complete the survey and return it to the researcher by mail. High procrastinating participants were identified by their degree of agreement with the survey on certain items. Interestingly enough, the researcher also measured the amount of time it took participants to return the survey. So this is when you're doing something sneaky in your research, not sneaky bad, just like really thinking about your issue. The following represents the number of days that some of the high procrastinators waited to return the survey. Is this group significantly different from regular procrastinators who typically return their survey within 2 days? So we are comparing the results of how long it took them, how many days they waited to return the survey, against a test of 2 days. Here's what we got. Now remember, 2 sample. It says it does not indicate which way we want this thing to go. So we do it as 2-way, 2-tail, or remember what I said, it's harder to reject with 1 tail sometimes. So you want to make sure that you cover your bases and do 2 tails. This survey, this entire study could go completely fluey and then he's got nothing. So n equals 10. Here's our mean, standard deviation, standard error. Test value is 2. Now remember, SPSS does not know what we are looking for. So it gives us a test statistic, and then it gives us our p-value and our point estimate for Cohen. H sub O, mu equals 2. This says that they're all going to return it within 2 days. H sub A, mu does not equal 2. They're not going to return it in 2 days. It's going to be different. With a 2-tailed test, you don't know which way it's going. Our critical value of T from the table with 9 degrees of freedom, plus or minus 2.262, run our study. This is our test statistic. This is our calculated value of T. We compare it, 2.272 and 2.262. We just squeak by with significance. And you can see our P is 0.049, just squeaking by with our p-value as well. Confidence interval, I'm not going to go over again where I got all these pieces from, but this is what it works out to. And we are 99, I think, oh yeah, I ran this as a 2, from the table, I got the 2-tailed value, critical value of T at 0.01, 99% confident that the true population mean falls between 0.239 and 14.639. So here's the thing. You need to realize that this is a really, really big range, right? So again, in the context of the problem, you need to say, okay, so we're pretty confident that, between 0, these high procrastinators return things between 0 and 14/15 days. Our effect size, we've calculated this enough, 0.718, and it's also in the printout. This is a large effect. So we've really got something here. Any questions? So the big difference between this one and the other one is that we ran it as a 2-tail. And when we run something as a 2-tail, we use both sides. We use these numbers on this side, 2 tails. Degrees of freedom, 0.01 or 0.05, whatever you need. Okay, and then the last example for the evening, if there's no other questions, we ask whether a new classic example. We ask whether a new version of our textbook is beneficial or detrimental to students learning statistics. On a national statistics exam, we already know that the mean is 80. We're comparing whatever happens with our new thing with 80 on other textbooks. A sample of students using this book has the following scores, and we're going to test this at 0.01. So again, nothing's changed here. Remember, you're going to put in the test value of 80, and you're going to get all this, the mean, standard deviation, and standard error. This is your T. That's a tiny t. You'll also start to notice as you go through these examples on your own, this is very close to 0. You're never going to reject there, ever. We have 9 degrees of freedom because we had 10 scores. And our p-value for a 2-sided test is 0.688. That's huge. So we are going to reject, and then our point estimate is here. Let's see, a mu equals 80, mu does not equal 80. Here's our critical value of T, plus or minus 3.250. T equals negative 4.15, and we fail to reject. And I give you fail to reject comparing the scores to the graph, and I also compare it to the p-value here. Okay, so that is probably the most extensive one sample t-test lecture I have ever done. So I've given you like everything. We've got confidence intervals, we've got 0.01 going on, we've got 0.05 going on for testing. Remember, the confidence interval is always two-tailed. That's a big mistake a lot of students make there. Everything is I think it's very clearly spelled out for you. So I'm going to say that if you're good, you can go. And if you have questions or you want to go through it or you want to do something, you let me know and we can stick around. Okay, so have a great spring break. That's the most important. You have things due at the end of spring. I'll have to move those dates so that you don't have things due in the middle of spring break. We'll have them at the end of spring break, and look for a lesson on power from me. Okay, that's it. Have a great spring break. Make good choices, as I'm telling my daughter who's going to Cancun. Hopefully y'all come back alive. Bye. Okay, Sim, do you have questions? Because Jackie actually made an appointment with me. You're on mute.
Okay, I think I was just stuck at the confidence interval because I found my way in the SPSS to change it from 95 to 99. And that was kind of throwing me off a little bit.
Yes.
So ignore that because
Yes.
we're not using the critical values from there. We're taking the t-value and looking at the table.
Exactly.
Ignore the confidence intervals, those numbers that it's giving entirely.
Right. Oh, I'm gonna stop the recording. Hold on.
Okay. And then you'll do the thing on the power. Was I completely off in the homework on power?
You know
I-
what? It just was more than I had done in lecture, and I wanted to get this stuff done first. So don't even worry about it.
Okay, cool. Because I was like, I think I was able to get, I have